So it is my pleasure to welcome, back to Caltech, Kim Boddy, who's a new assistant professor at University of Texas at Austin. Uh, Kim was a PhD student here back to 7 to 10 years ago.
Oh,
It's not that long. And before then, she was a student at MIT and did experimental nuclear physics. And I think like many of us realized that the best experiments happen out in space. So it's time to go look out in space. And came to Caltech, worked with Sean Carroll on theories of interacting dark matter, how they affect cosmology, and also the fascinating concept of Boltzmann brains, which we all know and love. Or I don't know, but I love the idea anyway. Then afterwards went off to University of Hawaii as a postdoc, and then to Johns Hopkins, working with our old friend Mark Kamiankowski in new directions on dark matter and new kinds of dark matter and observational consequences. And she's here to tell us today about the effect of dark matter, not just on local activity that we know and care about, but also how it influences the whole story of the cosmos from the beginning to the end. So great to have you here, Kim. Please go ahead.
all right. Thank you very much. I'm very happy to be talking to you today. I wish I could be there in person, but I hope I can come out and visit soon once we are all allowed back outside. So yes, the message I want to convey to you today is really this idea that we can actually do particle physics using cosmological observables, that we have information from early universe physics and later that we can understand how dark matter as a particle interacts with the standard model if it does. So this program that I'm about to present to you I've had a number of collaborators who I'd like to acknowledge here that I've worked with. These are undergraduate students at USC, now graduate students, though about to become postdocs, and at the time a postdoc. These are my more senior collaborators. I would like to note in particular, I've done most of this work, if not all of this work, with Veta Glusovic, and she was actually also a Caltech graduate student with me, and we roomed together in Caltech graduate housing in the Catalinas. So who knew that years later we'd come together and work on this really interesting science. So the story that I want to tell you today starts with the standard role of dark matter. So just to have everybody on the same page, I want to go over what dark matter's role is in the evolution of the universe, as well as how we view dark matter as a particle from the particle physics perspective. Then I want to take two sort of case scenarios about how we can understand dark matter properties from cosmological observations. And I'll do that using the CMB, the cosmic microwave background, and observations of the Milky Way satellites. And then I'll touch a bit on future prospects and where this sort of field is going forward from here. So let me start with the standard role of dark matter. Here is an illustration of the history of our universe. So shortly after the Big Bang, we have a universe that is very hot and dense. It's completely ionized. We have the creation of the light elements from Big Bang nucleosynthesis, which happens, a few seconds to a few minutes after the Big Bang. And in this time period, the universe is constantly expanding and cooling, and eventually the universe cools enough that electrons and protons in the universe can come together and form neutral hydrogen and stay that way. So in this process of what's called recombination, the ionization fraction in the universe, the amount of ionized particles, drops dramatically. So all of the radiation that was in the universe at this time was scattering quite often with, say, electrons. And once neutral hydrogen forms, these photons are essentially allowed to more or less free stream to us to be observed today. And this is the cosmic microwave background radiation that we observe. So we're observing things that are coming from an era, that was young in our universe's history. So once we have neutral hydrogen, we enter this era called the Dark Ages. And this is because there aren't a lot of optical probes that are coming from this era that we can hope to observe. But what's happening in the universe is very important during this time, because even though the universe at early times was very uniform and very smooth, and I'll get to that in just a second, there were small perturbations. So if you had an overdensity of matter, just a small overdensity of matter, that grows over time through gravitational interactions. And eventually they grow so large that they collapse into actual objects of matter. And they form these intricate structures that are shown here in purple. And you can have these clumps of matter that then go on to form galaxies and stars that we can actually observe. So it's not until this era of cosmic dawn, when the first stars sort of turn on, that we start getting observational probes again that we can hope to observe. So at this time of cosmic dawn, stars are formed and emit ionizing radiation and go out and reionize the universe. So all of this structure that has formed, all of these galaxies and stars that have formed and clumped together are observable today. And we can look at how they have clumped and how much mass there is and how much, what the abundance of different size objects are. And we can use that information to understand how matter evolved throughout cosmic time. So an important story to all this is going to be dark matter, and I will get to that in just a second. For right now, let me go back in time and look at the cosmic microwave background, because this is some really pristine data that we have from cosmology. So at early times, right, the universe, like I said, was uniform and homogeneous. And so the cosmic microwave background radiation is all mostly a uniform temperature. And we observe it at about 2.7 Kelvin. This is from an older satellite called COBE, but now we have the latest satellite, CMB satellite Planck, which has achieved a large amount of resolution in the sky. And so what you're seeing here in this map of the sky are little tiny fluctuations of the CMB photon temperature. And all of this is around, once again, this 2.7 Kelvin average value. So we can take this map of the CMB sky and cast it in terms of what's called a power spectrum. So this power spectrum is given as a function of multipole, and you're just taking your spherical sky and decomposing it into spherical harmonics. And so this is the L of our YLMs of spherical harmonics. And the important thing to remember is that larger multipoles means smaller angular scales in the sky. So Planck was able to have achieve a very high amount of resolution across the sky. And this is the temperature data of the CMB and the polarization data. And you can see for our best fit theory curve, this gray curve fits the data extraordinarily well. And these data points have extremely small error bars. So we understand the physics of what's happening here very well. So all of these bumps and wiggles are due to what are called acoustic oscillations. So in the early universe, before recombination happens, imagine that you have a dark matter over density here, and dark matter over density here. So this dark matter is going to create a gravitational potential well that is going to want to pull in ordinary matter, or for what I'll call baryons. So these baryons are going to see these potential wells and are going to want to infall. But the baryons, the protons, the electrons are all tightly coupled to the photons that are in the early universe. And so there's a lot of scattering processes that go on between photons and electrons and protons. So at the same time, there's what looks to be a radiation pressure that's wanting to push everything back out. So you can imagine that you have this system of dark matter potential wells and baryons and radiation across the universe at different scales. And this motion of wanting to fall into potential wells and getting pushed back out is just this simple harmonic oscillator motion. So this is the Fourier space description of what's happening in the early universe. And at the time of recombination, you can imagine freezing this picture at a given time. And whatever is happening with these baryons and with these photons moving in and out of these potential wells, that gets imprinted in the fluctuations of temperature of CMB photons. So this is what we're seeing when we see these oscillations here. So the best fit theory curve, this gray curve, comes from what's called lambda CDM. So lambda CDM is the most vanilla baseline cosmology model that we have. So in lambda CDM, we assume that there is this component of the universe, this fluid called dark matter. It's assumed to be cold and completely collisionless. So this dark matter behaves as ordinary matter, but doesn't interact with photons or with ordinary matter in any way. And we know from all these oscillation peaks that dark matter has to be about 6 times more abundant than baryons. So the picture that I was showing before is really depicting dark matter's role in the early universe. Dark matter is serving as the potential wells to create these acoustic oscillations that we see in the CMB. And so I mentioned this before, but when I say baryons, I mean protons. There's helium in the early universe, and electrons are tightly coupled to protons through Coulomb interactions. So by baryons, I'm including electrons as well. So anything that's non-relativistic ordinary matter at the time of the CMB formation. So if we want to take this story of dark matter seriously and ask ourselves, well, what is it? This, in cosmology, I just input some fluid component in the universe that behaves as matter. So maybe it's an actual particle, maybe it is matter. And how does it fit into the standard model if it is? This question kind of spawned a paradigm called the weakly interacting massive particle. So the WIMP is sort of the baseline model that we originally thought. It fit very nicely into other parts of particle physics that I won't get into. But in short, the weakly interacting massive particle has a certain amount of interaction with the standard model that's weak, and in a certain mass range will give you the observed abundance of dark matter that we see from that we infer from the cosmic microwave background. So this paradigm spawned a lot of search efforts. How can we see the interactions between dark matter and the standard model in sort of a controlled setting? So if you look at this Feynman diagram, or this Feynman-esque diagram, there's two dark matter particles, and they're going to, in some way, communicate with standard model particles. And depending on how you read this diagram, you can choose time to flow in a particular direction, and this will give you a standard search channel for how we look for dark matter. So for instance, we can have two standard model particles come and make dark matter, and then this is the production of dark matter that we can possibly see in collider experiments, for instance. The opposite direction is if we look in a place where we know dark matter to be in the universe, we can say two dark matter particles will come in and produce standard model particles through annihilation. And so this is indirectly detecting the presence of dark matter through its annihilation products. And so there are various experiments that can go out and look for such annihilation signatures. The channel that I want to focus most on today is this scattering channel, where we have a dark matter particle and a standard model particle that are going to come in, interact in some way, and elastically scatter. So this is steeped in the framework of direct detection. So in direct detection, we are here somewhere in our Milky Way galaxy. This is an artistic depiction of our Milky Way. We are enveloped in a larger dark matter halo. So the visible Milky Way is only a small portion of the total gravitational potential well that we are in. So we have dark matter that is surrounding the visible Milky Way, and we are moving in it. Dark matter particles are moving within the halo, and this is going to create, in say our laboratory frame, some WIMP wind. So dark matter is going to, the idea is dark matter is going to come in and hit one of the target nuclei in, say, a large detector of, for instance, xenon. And the experimental effort is looking for the nuclear recoil of one of these, say, xenon atoms from dark matter coming and interacting with this nucleus. So how often we expect this to happen, or the rate at which these interactions should occur, depends on a variety of things. First, we are dealing with dark matter particles that are confined to the Milky Way galaxy, and they have certain properties. There's going to be a certain density of dark matter particles that are in our neighborhood, and they're going to be moving with some velocity. It's going to depend on what the particle physics is, what interaction is actually dictating this dark matter coming in and hitting this nucleus. And then it'll also depend on the properties of the experiment. How well can experimentalists detect this nuclear recoil? What target nucleus are you even using in the first place? So all of this affects how sensitive a detector is going to be to this presumably rare process. So we have not seen any evidence of any interaction between dark matter and the standard model in this way. And so we cast limits in terms of the dark matter nucleon cross-section, here it's shown in centimeters squared, against the dark matter mass in GeV. So if you aren't familiar with working in natural units, a mass of a GeV is about the proton mass. So we choose a very particular interaction to draw these limits that we have. So this is an assumed spin independent interaction. So the dark matter doesn't care what spin the nucleus is, and there's no velocity dependence involved here. So these spin-independent direct detection limits are numerous. There are many more that have that I'm not showing on this plot, but it kind of gives you the sense for the effort that's continuing to search for this weakly interacting massive particle. There are a couple limitations to this technique, let's say. So there's something called a detection ceiling. If you imagine going to very, very large dark matter nucleon cross sections, right? then you can imagine that these direct detection experiments are going to lose sensitivity. So they want to be in very clean environments, and they want to get rid of as many backgrounds as possible. So they put their detectors deep underground. So there's a problem, though. If we want dark matter to come in and interact with this detector, we have to assume that it's going to ignore all the particles that are in the atmosphere and in the crust of the Earth to actually get down to the detector itself to create a signal. But if the cross-section is too high, then the dark matter is just never going to make it to the detector. So there is going to be some detection ceiling where these experiments lose sensitivity at high enough cross-section. There's also a mass threshold. So you notice that these experiments cut off at some low mass. They're all slightly different depending on the detector specifications. But the short story is that dark matter only has so much kinetic energy. It has to be bound within our dark matter halo of the Milky Way. So if its mass is too low, it just can't impart enough momentum transfer to a nucleus for experimentalists to actually read out that nuclear recoil. So they lose sensitivity at low mass as well. So far the story has been dark matter interacting with nucleons, with a proton or with a neutron. There is an effort that has come up in recent years to look for dark matter electron scattering. So by going to a lighter target, an electron, you can probe lower dark matter masses. So now the dark matter mass here is being plotted in MEV, and about half an MEV is the electron mass. So you can see the efforts that are being made from these different experiments, and overall just the order of magnitude on the y-axis here for dark matter electron scattering isn't quite as low for dark matter nucleon scattering. It's a newer program. So these two ways of trying to detect dark matter are very important, are very interesting. It has its limitations though. So in both cases, they have a mass threshold and they have a detection ceiling. And what I'm interested in is actually sort of doing this direct detection experiment, but using cosmological observables. So the exact same physics in the same sort of parameter space as direct detection, we can actually use cosmology to search for these type of interactions as well. And they're going to be in pretty different regions of parameter space that we haven't traditionally thought to look for. So now let me get into the effects of what dark matter physics has and focus on the CMB for right now.
Could I ask a WIMP question?
Yeah.
I want, for these upper limits that you showed, are these strongly dependent on the wind situation? So for example, if it's co-rotating or warped by the sun's gravity or something like that, are there experiments that it really matters that the wind happens to be 250 kilometers per second, or it doesn't matter?
Yeah, so I mean, it gets folded into the analysis. So all of the, if you want to do sort of the baseline analysis where you assume dark matter is this smooth halo that has, you know, a Maxwellian velocity distribution, you can pump out limits with that assumption, and that's typically what's done. The place where you can imagine having some sort of significant difference is if you are thinking like maybe there's a substantial amount of dark matter substructure that is passing through at the moment, or something of that nature. I don't think that the gravitational effects from just the sun are going to make that big of a difference in terms of either its velocity distribution or its density on Earth. I think the much more important aspect is possible substructure that may be missing from the analysis.
Okay, thanks.
Mm-hmm. Okay, so now I want to talk about the effects that dark matter physics has on the CMB, which in cosmology is assumed that dark matter has no actual interactions. So the idea here is small scale suppression. And you can imagine, looking back at our dark matter potential wells, that now there are actual dark matter particles here that are creating this well. And if you have a baryon, a photon, a proton or an electron come in and hit one of these dark matter particles, it can eject it from its own potential well. And if this happens over and over again, if there aren't that many dark matter particles, or if this is a fairly small and weakly bound structure, then you can imagine completely destroying it, right? In sort of more cosmological terms, you have this dark matter fluid and this baryon fluid, and you allow them to interact with one another. And this interaction is going to cause a drag force that sort of couples their motion. So this fluid moves and it has an effect on the other. So whether you look at it through a particle physics description or through a more fluid, cosmological fluid description, the answer is that you get this suppression of small, loosely bound structures. So now the question is that given that this should happen, what sort of, how is the dark matter particle physics really coming into play here? So for the different types of models of dark matter, what I'm going to do is I'm going to parameterize the cross-section in terms of some constant times the relative velocity between my scattering particles to some power, right? And this phenomenological form actually covers quite a bit of models. So if you have, n being greater than or equal to 0, this is sort of a heavy mediator model. So for n equals 0, for those of you who are more inclined to look at Lagrangians, this just looks like a very simple Lagrangian. It's a point-like contact interaction. And you can incorporate velocity dependence or momentum dependence to get these n equals 2 and n equals 4 sort of cases. You can also imagine that dark matter interacts through a light mediator. So here I have dark matter and I have a pair of nucleons that it's interacting with. And if I don't assume that it's just some kind of point-like contact interaction, there's actually a particle that's being exchanged here. And so this light mediator can cause this cross-section to have a negative power velocity dependence. So for instance, n equals 2 corresponds to a situation in which dark matter looks like it has an electric dipole moment. If n is equal to -4, then this is a situation in which dark matter may have a very small electric charge. This is called millicharge dark matter. And it will feel Coulomb interactions with ionized particles in the standard model. So all of this is parameterized in this way, and cosmology actually cares about not just calculating the cross-section, it actually cares about what's called the momentum transfer cross-section. And the idea is that if you have two particles and they far forward scatter, so they're coming at each other head on, and they pass through one another, essentially. It kind of looks like that there's no interaction that occurs. There's no momentum exchange that happened between the two particles in this case. So it looks like nothing happened. It doesn't change cosmology. So you weight out that far forward scattering and preferentially weight backward scattering, where you have the most amount of momentum transfer. So this is the quantity that cosmology actually ends up caring about. So depending on the value of n, you have these correspondences to these different models. And then you can say, okay, well, now I need to go and look at my fluid equations for cosmology, insert a collision term in my Boltzmann equations, and I'm not going to show you any of that. Instead, I'm going to show you what it looks like, what the impact is on the CMB. So here's the CMB power spectrum. This is the case that I showed you before that fits the data very well. This is the lambda CDM cosmology. And if I turn on a lot of interactions, for instance, for a particular model, you can see this, this drastic effect that it has on the CMB power spectrum. So there are tiny things that happen. You can see an enhancement here. The maximum of these peaks shift, but the main effect, the effect that is actually going to drive the constraint is this suppression at small scales or large multipoles. And so this depends on what particle physics model you choose. So essentially what velocity dependence, what power law velocity dependence I chose. So different velocity dependencies will have a different effect on what the CMB power spectrum looks like at the end of the day. So I mentioned before that the momentum transfer is the thing that cosmology actually cares about. And so I wrote down for you this, this momentum transfer cross-section. But even at that, that's not really what cosmology cares about. Cosmology cares about the rate at which you transfer momentum. So here I've written down the rate of momentum transfer. This A is just a scale factor of the universe. Here's N sub B. This is the number density of target particles dark matter has to scatter with. This is the same sigma up here. And we have the dark matter mass, whatever mass particle, whatever particle dark matter is scattering with. That's this mass here. And then we have the temperatures of the baryon fluid and of the dark matter fluid. And the differences between the models comes in the form of this N here, which appears right here. So I want to plot for you the momentum transfer rate over the expansion rate of the universe as a function of redshift. And so the thing to keep in mind here is that this redshift corresponds to about when the CMB was formed. And this higher redshift or earlier times is going to correspond to essentially the maximum redshift that the Planck data is sensitive to. So I'm going to set this sigma naught, I'm going to cheat a little bit and say I've already fit everything to the CMB, and I'm going to set this at its 95% confidence level upper limit. And this line here drawn at 1 is showing you where scattering is efficient. So if you are above this line, that means that there's a lot of momentum transfer. If you are below this line, it means that Hubble expansion is winning. So the particles don't get to interact because the universe is expanding. So we can plot the different values of n, and going from -4 up to 4. And you can see that for these positive powers of velocity, you get a lot of scattering at high redshift or early time. And so this corresponds to earlier times corresponds to higher temperatures, which corresponds to higher thermal velocities in the universe. And so the cross sections here are quite high, and then they drop off as the universe cools. And it's not until you get to this situation of v to the -4 that you actually get a change in the slope of what this momentum transfer looks like. So at early times, you actually have pretty feeble interactions, and they grow at much later times. So I wanted to show this plot because it's indicating something important. It's all these lines are sort of clustering at a particular redshift, right? And this is just reflecting the fact that the data that we have error bars. And so there are going to be certain scales or certain multipoles at which the error bars are the smallest. And so the data are going to be the most constraining. So it happens that all of these lines are clustering at this particular redshift, about 2 times 10 to the 4. And the data are demanding that this momentum transfer be about, 0.1 of the Hubble expansion rate of the universe at this time. So, so this is going to allow us to kind of understand the behavior of the limits that I'm going to show you on the next slide as a function of dark matter mass. So essentially, what the CMB, you can kind of crudely distill this information that I'm about to show you into saying that the universe, that the Planck data is demanding a very specific amount of momentum transfer at a specific redshift, and that particular value is going to be that at which the Planck data can't describe the cosmology anymore. So, given that, let me go ahead and show you a more helpful picture in terms of what we're used to seeing in particle physics. So here's the dark matter proton cross section in centimeters squared again, against the dark matter mass for these particular velocity dependencies for these different models. And so the CMB excludes anything that is for this particular model that is at this line and above, right? So this can span quite a large range of masses. In principle, it can go up to arbitrarily large dark matter mass, and there's a nice scaling relation that you can determine at higher dark matter mass. You can't go to too low of dark matter mass, or dark matter starts behaving as what's called warm dark matter, where it has some non-trivial thermal distribution. So then it's no longer cold dark matter, it's instead warm dark matter. So we have a line that's drawn around a keV to 10 keV that this transition happens. And so this particular analysis can't look at anything lighter. So this is dark matter proton, and of course we can do the same thing with dark matter electron scattering. And the thing to note is where these lines kind of change their slope. So here on the left plot, you can see that the curves kind of kink at a particular location, and it's at about the mass of the proton. So for dark matter that has a lighter mass than the proton, it has a fundamentally different behavior than if it has a larger mass than the proton. Here, the story is the same, except the relevant mass is the electron, because that's what we're scattering with. So dark matter has a different behavior, a different scaling with mass. These limits have a different scaling with mass if dark matter is lighter than the electron versus if it's heavier. So this is all well and good. It would help to have a little bit of context in terms of what I was telling you before about how we typically search for dark matter interactions in particle physics. So let me, in both of these slides, just take this velocity independent, this v to the 0 case, because that is what we were dealing with before with direct detection, and show you what these curves look like in comparison to the direct detection bounds that we have. So here are our CMB lines for this particular scenario. And this dark matter proton cross-section over on the left is at really, really high values in comparison to direct detection. So the direct detection plot I was showing before didn't even show this part of the data, right? They were going down to 10 to the minus 46 centimeters squared in direct detection. So these are really high cross sections that the CMB is able to probe. This is the approximated ceiling that I was talking about for direct detection, above which they lose sensitivity. So there's a gap between what the CMB constrains and what direct detection is constraining. The CMB does get into this lower mass range, which is nice. But once again, it's at pretty high cross section. These are constraints coming from a different, looking at data, analyzing data from an X-ray quantum calorimeter experiment that is able to rule out very large cross sections of dark matter with us for larger masses. For dark matter electron scattering, the story is slightly different. The direct detection experiments are newer, and so they haven't achieved quite the same level of sensitivity as the nuclear recoil experiments have. And so this CMB line actually comes and intersects with the line that with the data that we have from direct detection. These lines also have ceilings, but they're just not drawn here. So this is the story for the CMB, and I will pause really quickly if there are any questions before I move away from the CMB itself. Okay, so now I want to change observables and look at the Milky Way. So before we had this story of this small scale suppression, and if you destroy structure at early times, then those sort of overdensities of matter no longer exist in the early universe to then eventually, accrete more matter and grow and eventually collapse and form actual gravitationally bound objects that we have. So this is a simulation of some larger host dark matter halo or some collapsed object of dark matter. And all of these dots are what are called subhalos of this larger structure. And so this is showing you that there's a lot of intricate substructure within this larger dark matter halo. But if you have this small scale suppression, very generically, it will just wash out any of this small structure that existed over here for just lambda CDM. You no longer see it here. To put it in a more quantitative way, we can understand the distribution of matter in the universe in terms of the matter power spectrum. So here it's showing you essentially how much matter there is as a function of scale. So the scale is in inverse megaparsec. And this line here is showing you what the matter power spectrum looks like for lambda CDM. And these blue and red lines here are showing you what happened if we turn on this interaction that scales as v to the 0 or v squared. And you see that the matter power spectrum is expected to peel off. So there's less structure at higher K or smaller scales. And you get this weird oscillatory behavior at very, very small scales. But we have data here. We have experiments that have gone out and observed structure, and we have structure at these small scales that we have observed. So given that, the models that I've shown here, these are plotted at the CMB limits, should be ruled out by the very fact that we have observed galaxies in our visible range. So we can imagine taking the smallest structures that we've seen, right? Because this effect just gets more and more pronounced as you go to smaller and smaller scales. So you would imagine that the smallest object that we can see will have the greatest constraining power for our particular model. So this is this now leads me to look at things that are close to the Milky Way, so things that are close by, but very faint. So they're going to be small dark matter systems, and they're faint because they don't have the mass to sort of accumulate enough visible matter to create very luminous galaxies. So here's our Milky Way, visible Milky Way, our larger dark matter halo of our Milky Way, and these are all subhalos that host galaxies. And these galaxies are dwarf galaxies. These in orange are ones that we've known about for a while. The ones in blue are ones that were identified with the Sloan Digital Sky Survey. And more recently, the Dark Energy Survey has seen a lot more of these satellite galaxies, and a lot fainter, so getting to lower and lower mass. So how does this play out in sort of our interacting cosmology? So here I'm showing you the matter power spectrum again, but I'm dividing out the power spectrum for lambda-CDM. So if we just had lambda-CDM, this would be a straight line at 1. But given that we have this interacting dark matter, depending on what cross-section we set it to, it will cut off more and more small scale structure. So the higher the interaction is, the more that structure is suppressed. So there are a handful of things that go into this sort of analysis. So the CMB was nice. The CMB we understand really well. We can write down equations for it. We have numerical solvers that can solve things and fit the data really well. When we start talking about collapsed structures like actual galaxies and halos of galaxies, there are nonlinear effects that come into play. So given a halo, we need to understand the population of subhalos that are going to be confined or gravitationally bound to the main halo. So, what is the distribution of these halos of different sizes, of different masses? And this information comes from simulations. So once we have that information, okay, so now I have a subhalo, right? But that's not telling me anything about the actual galaxy it's supposed to host. So there's, we have to model how we put in a galaxy given a subhalo of a certain size. And so once we put all those pieces together, then we can say, okay, given how luminous the Milky Way satellites are that we observe, we're going to take our model and fit the data, and from that we're going to be able to constrain this cutoff of the matter power spectrum that we're seeing from an interacting dark matter model. So the interesting thing about this is that there are a lot of different models that actually give cutoffs of the matter power spectrum. So this is a pretty robust tool. You can look at different models. I mentioned warm dark matter. There's also something called fuzzy dark matter. And instead of the cross section here determining whether where the cutoff of the matter power spectrum occurs, it's the mass of the dark matter. So we can understand in these models, we can place constraints on the mass of the dark matter particle, just based on how this power spectrum falls off from the lambda CDM case. So given that we have observed satellite galaxies, we can say, all right, we can't suppress structure in the early universe enough such these galaxies are not able to form. So let's go back to our direct detection picture that we were looking at before. So this is the plots. These are the plots that I showed you for dark matter proton and electron scattering. And if we now look at the Milky Way satellite abundance restrictions, we get a lot more constraining power from this. So over on the dark matter proton cross-section side, we're doing orders of magnitude better than the CMB. And same thing here as well for the dark matter electron scattering. So this has provided a lot of constraining power for this type of model. I showed here a very particular case of n equals 0. The velocity independent scattering case is easy to deal with. I'm not going to go into too many details, but I just want to show you how velocity dependent models kind of complicate this picture. So once again, this is the matter power spectrum normalized to lambda CDM as a function of scale. And you can see that these power spectra have large oscillations at very small scales. So this really didn't happen before in the other picture, in the other scenario I was showing you before. So this complicates things quite a bit. But there are ways to get around this and come up with estimates for what the limits should be. And for these different cases, I won't go into detail for them, but we can constrain these n equals 0 to 4, 6 cases with Milky Way satellites as well. So in my remaining few minutes, I just want to comment on sort of the future prospects of this type of research and what cosmology has to hold for us in terms of understanding what dark matter is. So as far as the CMB, we've come a long way since Kobe, and we've have this exquisite map from the Planck satellite. These were all space-based telescopes. The benefit to having a ground-based telescope, though, is that you're able to build a bigger telescope. And so you're going to be able to resolve smaller angular scales in the sky. So we have the South Pole Telescope and we have the Adhikari Cosmology Telescope that have been operating. And these are able to resolve these smaller scales and help further constrain dark matter interactions, which have a prominent effect as you go to smaller scales. In the future, we have Simon's Observatory and a little bit later CMBS-4 to look forward to. And to kind of give you a sense for the level of improvement that we expect from the CMB, going from Planck to CMBS-4 will give about an order of magnitude-ish improvement in the constraining power. So there are also other experiments as well that have been proposed, especially because we recently had the Astro 2020 Decadal Survey, where everybody's laying out the plans for the next 10 years in the astronomy community. And so if future instruments are built, then certainly they will do better in looking for these sorts of effects that dark matter can have. From the galaxy survey side, I showed you, what we've been able to see with the Sloan Digital Sky Survey and with the Dark Energy Survey. The next generation in this line of telescope is going to be the LSST at the Rubin Observatory. So we'll be able to see much fainter and smaller galaxies, satellite galaxies of the Milky Way. And this is really our opportunity to further test this idea of looking for this possible cutoff in the matter power spectrum. And once again, this cutoff could come from all sorts of different types of dark matter models that would give this prediction. So going forward, this line of observation is going to tell us a lot about the structure of dark matter that exists today. There are plenty of other galaxy surveys. I just chose the ones that I've interacted with the most. But this certainly isn't the end of the story. There are a lot of cosmological observables, and they all complement each other in a particular way. So here is just a rough depiction of how different observations relate to one another in terms of cosmic time that they probe and the physical scale that they're observing. And so here we have our CMB blocks that are at both high and low redshift. They tend to probe larger scales. These are our dwarf galaxies that I showed you before, but there's also other options as well, even beyond the ones that are just being shown right here. There's a really interesting story with 21 centimeter cosmology and even other lines as well that you can do that I don't have time to tell you about today, but I'd be happy to talk more about it if you'd like. So, these different observables probe these different scales in these different eras. The important thing to keep in mind is that they all have different systematics. And so even though I showed you constraints for this particular dark matter proton or dark matter electron scattering, and the Milky Way satellite constraints just, blew the CMB constraints out of the water, it's important to remember that when dealing with things that have collapsed, there are going to be a lot of systematic errors involved. And you want to be sure that you're telling a consistent story throughout cosmic time, right? So if you have a particular model, it's important to understand what's happening at these different scales at these different times. And so different observables are going to be sensitive to different types of dark matter models. It's not always true that the CMB wins out over the dwarf galaxies. And it's important to keep this line of investigation open for hints of new physics that might not be quite what we were thinking, but will give indications that there's something in the dark sector that has to be happening. For instance, if there's a cutoff of the matter power spectrum, that doesn't necessarily mean it's going to be this dark matter proton scattering story. But if we do observe it, then we can go and ask that question and ask, what else, what other handles can we have from cosmology that will help us understand what the model is. And so this kind of brings me to this, what else is there? There's this model discrimination that I talked about, but I also showed you a very specific case, this very specific dark matter model in and of itself. I assumed dark matter was a particle and that it was in a certain mass range. It was kind of WIMP-like, except not weakly interacting. So there are certainly other models that exist and can give different signatures over these different cosmic observations. You can also have a completely different underlying cosmology. I just modified the basic lambda CDM cosmology, and it could be that something else is happening, in the very early universe that has an impact on how dark matter forms. So this is to say that it's going to be really important going in the future to have some sort of system that really brings all these observations together in a coherent manner. And so this is, the story that I want to convey, and this is the line of research that I've been pursuing on trying to take different probes and fitting them all together so that if we do observe something anomalous in a particular system, we definitely have the tools to go and explore that further, given all other cosmological probes. So let me go ahead and summarize. I showed you this story with dark matter scattering with protons and electrons in the early universe. The short story is that it suppresses structure at small scales, and you can look for this or constrain it with the CMB. And you can constrain this suppression with the abundance of Milky Way satellites or any sort of small galaxy that may be observed through other means as well. And that cosmological observables are going to provide complementary tests of dark matter, not only with themselves, but with the terrestrial experiments that we have. And that's the story that we have so far. And there's a lot of interesting routes to go, and new telescopes and satellites that are coming online that are going to make this story much more rich. So I'm happy to answer questions, and thank you for listening.
Thank you. So we'll take questions now. If you raise your hand, I'll unmute you, and then you can go ahead. Shri, you can unmute yourself.
Yeah, I had one question and one comment, which is, and you have to please bear in mind I'm a what you might call a vanilla astronomer, not very sophisticated about these matters. So it appears to me that you showed a slide, I think it's slide 11, which had cross section on one axis, mass on the other.
Mm-hmm.
And various people, I mean large number of people, are engaged in a thing where they say, here's something I'll do. I have xenon or gallium, I have something else, and they'll draw a line, and above that is excluded. This seems to me a kind of a Wild West approach to science. And I'll end my question by the comment. Let's say I'm God, which I like to be anyway. And I magically come and tell you, I'm that whole phase space about 10 to the minus 40 or below 10 to the minus 40 square centimeters, and above 1 MeV, it's excluded. Have you learned anything?
Sorry, can you say that again?
Well, two questions were, this just seems kind of like a wild thing where different people have their own experiments and they exclude.
Right.
And so one can spend entire lifetime excluding things. Have you learned anything?
Yeah, no, that's very true. I mean, the goal would be to actually observe, of course, and that's that's direct detection's main thrust. There is, maybe playing off of your comment a little bit, it's not necessarily that this has to be the picture, this has to be the universe that we live in, right? We're making a strong assumption that dark matter interacts with any sort of strength with the standard model. It may be that it doesn't.
So does that mean this whole field, you can basically shoot around and at the end of one's career have really no paper because it's all upper limits? That seems rather sad.
Yeah, I mean, at the moment, that's what we have. We have upper limits. I mean, on the one hand, we definitely know that there's dark matter, right? We definitely have a lot of information about its properties gravitationally, and this is sort of the particle physics desire to understand what it is. And at the moment, the floodgates sort of opened as this WIMP scenario was ruled out more and more in terms of, well, what else could it possibly be? And so, theorists were to keep us employed, and we're very curious people, and we like different models. And so there's been a lot of scenarios that we've come up with. So in terms of, what have you learned from this particular search or this particular analysis, is all heavily model dependent. Is that sort of what you were going towards? I mean,
no, that's fine. Yeah. I mean, thank you very much for a rather, I would say, intellectually honest answer in a field I normally don't hear such replies.
Thanks. Any other questions? I have several questions. Since I'm the host, I can ask a few. I've always wondered about this. We always worry about this effect of dark matter on dispersion of gravitational waves and things like this. In the models, I haven't followed the last few years, but there used to be a lot of excitement about self-interacting dark matter and the shear and bulk velocity, viscosity terms. Is that, has shear viscosity been completely cast off due to bullet cluster, et cetera, things, or is that still on the table?
This would probably be a question best suited for Phil. The self-interacting dark matter story is still very much in the picture. It's still very actively researched. I'm not sure about, in particular, the shear question. But even the space of the standard self-interacting dark matter scenario has grown in terms of different possibilities. Sort of the Spergel-Steinhardt original thought of self-interacting dark matter was just this hard sphere scattering scenario and looking at how it changes the shapes of galaxies or halos. And this has evolved into, well, what's actually controlling this self-interaction? Does it have a mediator? So if a mediator now exists, is it light enough that it's going to induce some sort of long-range interaction with dark matter? So the story has only gotten bigger, in short. So it's very much still a thing. It's still very much research, and simulators are doing a much better job at coming up with ways of trying to capture this physics to understand how it impacts the formation of halos.
I see. Thanks. Last call for questions. Anybody else? Seeing no takers. Let's thank him again. Very nice talk.
Thank you.
And feel free to stick around for a few minutes if you want to wait for everyone else to leave before you ask your really biting questions.